Okay, well, I think now we're going to do a full example. So to see how these elimination matrices work, and to solve this, we could just do our row operations on this without going to matrices, but we'll use it as an excuse to see how to use these to put this into matrix form, and also not just to solve it, but to sort of save our Gaussian elimination into matrices. So this is really what this is. It's storing the process of Gaussian elimination. Why would you want to do that? One reason, you may have different right-hand sides. This may need to be repeated many times, and you don't want to do all the steps every time. You've done the work, save it, and then you save a lot of time. So this is the idea here. So first we'll put it in matrix form. So let's call this, let's call A would be equal to, so this is also, we could write this AX equal B, where A is 1, 0, 4, 2, minus 1, 3, 1, 1, 7. X, I guess I'll put a little bar over it so that we know it's not this X. X, Y, Z, and B, probably should get a bar. 2 is just 6, 0, 4, okay? All right, so this is the same thing. So one thing I can do, I don't need to write all these letters all the time. I want to get rid of that. So what I want to do is find a matrix that I multiply A by that will put it in the upper triangular form I want. So the goal is we'll find, so you don't have to question why we're doing this yet. I know it might seem like extra stuff, and it probably is for this case, but we want to work at something that we can take with us for something bigger. So we want to find E so that EA equals U, and U is upper triangular. And by this we mean, what do you think the definition of upper triangular means? So U is upper triangular means, so U is upper triangular, I will abbreviate it, if any U below the main diagonal, so if Uij equals 0 when, let's see, when the row is bigger than the column. Okay, so when I is greater than J. Okay, that's the definition of upper triangular. See, the bigger rows would be the bottom triangle, right? Okay. So I want to find a matrix E square 3 by 3. So when I multiply A, I get an upper triangular matrix U. So we'll do this sort of like at the start of the last video. We started to hint at how you do this, and we'll do this now. So I think you already know the first matrix that will make these two 0. So first we'll just start, we'll zero out one column at a time. So we'll proceed solution. So find E1 so that E1A has zeros in column 1 below row 1. Okay, so that's our starting point. Then E2, so E2, E1A has zeros in column 2 below row 2. Okay, so let's try to do it. So you see there's the matrix. So I think we need E1A is equal to, I need, I'm writing here, but I'll move this up. I need minus 2 times the top one plus the second, and then I need minus 1 times the top. So I don't change the top, and then I need minus 2, 1, 0, and then I need minus 1, 0, 1. So that's E1, and I'll write A here. And you can see, let's actually do this and see that it works. So this row times these leaves me the first row, so I get 1, 0, 4. This row, when I multiply by this row, I get minus 2 times the top row, 1, 0, so I get 0. Minus 2, 0, 1, minus 1. No effect here, so minus 1. Minus 8 and 3, minus 5. And the last one, minus 1 times this top row plus the bottom row. So I get 0 as I wanted. I get 1, no effect because of the 0, and I get 3. Minus 1, 4 plus 7, 3. So that's E1A. And I'm almost there. I want to now find E2. So let me write it here so that I remember it. E2, E1A. And what should I multiply E1A by now to get? Right, I want to just multiply it by 1, right? I want to add the second row to the third row. So I can do that with this. This will leave the first row, this will leave the second row. And now I want to take 1 times the second row plus the third row. Okay, and this is going to give me my final U. So I have 1, 0, 4, 0, minus 1, minus 5, and I add, so I have 0, 0, minus 2. Okay, and this is U. Okay, this is U. Okay, all right. Now, why do we do all this instead of just solving? Well, I want to show you that now I can write A as a lower triangular matrix and times U, okay? So, first of all, okay, so we have U. So we have U. And we have E2 and E1. A equals U. Okay. Well, so let me write this out again. So I have E2, E1, A equals U. If I write this out, I have 1, 0, 0. And what was the other one was 1, 0, 0. And here's my A. And here's my U. Okay. E2. E1, A, U. All right. Well, if I know the inverse of E2, if I know a matrix, I can multiply E2 by to make it go away, to make it become I. I can multiply on both sides by the same thing, and that should not change anything. So my question is, what should the inverse of E2 be? So, question, what matrix is the inverse of E2? So this means find a matrix E2 inverse. So E2 inverse E2 equals I. Because I know if I have I does nothing, right? When I multiply a matrix A by I, it does nothing. So if I multiply on the left by E2 inverse here, this will sort of make this will neutralize this. It'll turn it into 1. So this is analogous to say if you have 5x equals 7, so this is the same thing. I could I multiply on the left by 1/5, 5x equals 1/5 7, to simplify it to get the expression. Okay, so this is it in one dimension. And we want to go all the way and do this now in 3 dimensions here in matrix, with matrices. So what does E2 do? E2 takes the second row and adds it to the third row. So whatever it multiplies on the right, it takes the second row and adds it to the third row. So to undo that, I should take -1 times the second row and add it to the third row, and that will undo the change I just did. I just added the second row. Now I subtract the second row. You can't undo it, but you can nullify it. So E2 inverse is equal to 1, 0, 0, 0, 1, 0. It doesn't do anything here, E2. So I don't want the inverse to do anything and mess the first or second row up. But for the third row, I want this. Now usually you can't figure out an inverse by inspection like this, but with these you can. You can just say, well, what is the action of that matrix? Let's undo it. Now, you try. What do you think E1 inverse should be? Well, E1 took -2 the first and added it to the second. So I should take +2 to undo that. And it took -1 times the first row and added it to the third. So I should take +1 to undo that. Okay, so that's E2 inverse and E1 inverse. So now by multiplying both sides of this equation on the left and the right by the same thing, I can isolate A. So we have, I take E1 inverse on the left, then E2 inverse. That will undo E2. And this becomes I, or goes away. This becomes I again, or goes away. But remember, this was equal to U, so on this side, I also have to multiply in the correct order. And I have isolated A into E1 inverse, E2 inverse U. And in fact, this is lower triangular. As you could see, these are both lower triangular. They have nothing above the diagonal that is non-zero. And if I take their product, I get something that's lower triangular. So I can say this is equal to LU. This is the famous A equals lower triangular